The basic stuff tonight. So let's get started. All right, so first of all, who is familiar with the OSI model? Anybody heard of the OSI model? Dan's raising his hand in the hallway.
Yes. I kind of know it.
All right. No one in here? Good, that's what we're talking about. Anyone recognize this model? This is the TCPIP model. All right, you got a hand in the back? Cool, so there are two different models that are generally used to express how networking works in computing. One, as you saw before, is the OSI model, which stands for Open Systems Interconnect, something like that, and TCPIP. And they're pretty similar. They have some overlap, but they have different use cases. Generally, you'll see more widely used the TCPIP model since it's more simple, and you can see here the top three layers of the OSI model are condensed into the one big application layer of the TCPIP model. But the distinction is made here. It's not that important really, but there are some cases where you can distinguish between these three layers here. And I'll go back to that first slide real fast. So I'll just briefly gleam over what these all mean. So at the bottom layer of the OSI model, we have the physical layer, which is like your, it's the medium that the data is that's transmitting over. So it could be your the radio waves in the air, it could be the Ethernet cable, or it could be optical. Whatever the medium is that you're transmitting over, that's the physical layer. So the data link layer, this is where MAC addresses come in, and we'll talk about that in a bit. But that's sort of the layer at which things on a local network kind of communicate at the low level, and we'll get into that, and the level at which switches operate at. Above that is the network layer. The one you probably most commonly hear about. This is where IP addresses are at the network layer, and this is where all the routing is done, and this is where your router operates, network layer. Above that, it's transport, which deals with the connection or lack of connection, and we'll talk about that. Session and presentation are a bit, as I said, they're not as commonly used, but here at presentation, you'll talk about encryption, and session, you'll get things like sometimes SOCKS proxying and some niche stuff like that. And finally, at the top is application, which is one we're exposed to most frequently, which is things like HTTP, the language your web browser speaks to the server. So going on, we've seen how they both models look here. Oh, and I should mention down here in the TCP/IP model, they call it host to network. I think it's more commonly known as the link layer in this model, but I've seen different diagrams show it different ways. Anyway, going on. So this is a Jake quote, actually. Internet versus internal. Yes, the first 6 letters are the same. Oh, how do I make this thing auto image? There we go.
It doesn't work. It never works.
Really? It worked last week. Yeah, okay. There we go, okay. So just to make a distinction here early on before we get into more detailed stuff, we want to talk about the internet versus internal networks very differently. So the internet obviously is usually out of your reach. It's what's going on across the world. And your local network is a private network. That's the devices that are connected to your switch or your wireless access points, things that are very hyper-local to what you're doing. And that's kind of important when we talk about some things later on here. It might seem obvious, but not always is. So first of all, we're going to talk about MAC addresses. So you've probably seen them before, but they have nothing to do with Apple computers. I see that a lot where people are like, well, I don't have a Mac. I have a Windows computer, so I don't have a MAC address, right? But that's not true. All network adapters have MAC addresses, and they are uniquely identified by MAC addresses. And there are 6 bytes that are allocated for a MAC address, so that means there are 2 to the 48 possible unique MAC addresses that a device could have. And that gives us plenty of space to avoid any overlaps when devices are made. The first 3 bytes are for the vendors, so anything made by the same company will have the same, usually the same first 3 bytes or a variation of them since they can have multiple of those. That's called the OUI. So like anything made by Linksys will have the first same 3 bytes. And then the last 3 are uniquely identifying that particular network adapter. And these addresses are only relevant on your local network, so beyond your gateway, no one can see your MAC address and no one really cares about your MAC address. It's only between one device and the next one on a local network, which is pretty important here. And so when you plug into a switch, back in the day when hubs were more common, everyone would plug their computer into the hub, and all the traffic would go out all the ports. And you could plug into the hub and sniff all that traffic if you wanted to. Switches kind of solve that problem by they learn which MAC addresses are plugged into which port on them, and they only send out traffic for that MAC address on that port, which avoids that most risks of sniffing, and also lightens the load on each host in the network. And so how this works is over here we have an Ethernet card pictured there. This card is listening for traffic that's destined for its MAC address. Everything else, it can just drop it since it knows it's not meant for that device. It can ignore it, which makes it easier on the kernel and the operating system, so they don't have to parse through all those packets. A lot of it's done in the hardware level here. The thing about MAC addresses, though, even though they are unique to that device, they can be changed and spoofed very easily. There's nothing stopping you from changing your MAC address. Nothing wrong with doing that either. There's lots of legitimate uses for that. A lot of mobile devices nowadays will actually change MAC addresses randomly while scanning for networks, since there have been concerns about people being tracked by their MAC address. And so your phone's always sending out probes with your MAC address looking for networks. People could use that to track where you've been at. And actually, someone did a presentation last year. Jeff did a presentation on an application that can track people by their MAC address, so that's something to look into. But in short, it can be changed, and it's pretty easy to do so. So it should not be used as a form of authentication at all, ever. And you're probably more familiar with Internet Protocol addresses or IP addresses. These are used to communicate across the internet as well as on your local network. And they are routed across the internet, and we'll talk about routing in a second. But same as MAC addresses, I didn't mention it for MAC addresses, but you can't have more than one of the same on the same local area network. Otherwise, you get conflicts and things just don't work and behave in unexpected ways. I've seen it happen before. You'll have two servers that are sharing the same IP address on accident, and every time you try to request the page, you get a different version of the page, and you just spend hours confused why it's not working correctly. That's why it's important that they're different addresses. And we'll talk about private ranges in a bit, but obviously a lot of networks share the same ranges, but they're private, so that doesn't matter as much. And it's important to note that a network adapter is not limited to just one address. You can have an arbitrary number of addresses. In fact, you can have as many as you want until your memory runs out on the system, at least as of Linux 2.2. And over here on the right, you've probably seen IP addresses before, but here's an IPv4 address, which is now kind of getting phased out in a way. So it seems pretty familiar. 32 bits of data, or 4 bytes. The new way is IPv6, which is still not too widely used, unfortunately. Hopefully we see more of that coming out soon, but right now it's still pretty limited, but it's way larger. I think that's 16 bytes of data instead of 4 bytes. And so the issue we have with IPv4 is that these are easily exhausted. I believe that, I don't know the statistics, but we're almost running out of IPv4 addresses. Whereas with IPv6, the likelihood of running out is very, very unlikely. So that's why we're kind of moving on to those for more space, less exhaustion. Any questions so far on this stuff? Any questions at all? All right, going on. So network masks. So a lot of times you'll see after a network address, you'll see a slash and a number, or you'll see one of these things like 255.255.255.255. Well, those are network masks, and they tell you how much, what space of that particular subnet is available for use, essentially. So we'll see here that a net mask of all 255s or all ones in binary is just one host. A network that is a /32 or that can only have one host on it. Not very useful. Moving on to this, most networks that you use in your house are probably this net mask. You might have seen it before, 255.255.255.0. That's called the /24, and that means you can have 254 hosts on that network. And I'll show you here. The way this works is that if we look at an IP address, there's the 4 bytes. The net mask tells you which bits of those not to change, or which bits don't change for all the devices in the network. So if we have a net mask of 255.255.255, that will mean that these first 3 bytes, they're the same for all devices on the network. Unlike when it's all 255s, the entire net mask is all ones in binary, and you'd have all of these be the same across the entire network. But going on with that, another one that's used on larger networks in companies and at Iowa State you'll see is a /16, which is 255.255.0.0. That's a very large number of hosts, 65,534 hosts on that network. And lastly, a /8, which is a whopping, can't really tell what, 16,777,214 hosts. And you'll notice that each one I'm saying minus the broadcast and network addresses, and I'll mention that in a second as well, kind of out of order here. So examples of these netmasks, you may have seen these on your computer when connected to the Wi-Fi, but Iowa State's internal network is 10.0.0.0/8, which means they have a very large number of hosts that they can put on their internal network. However, you'll notice that if you look at your computer's configuration, you will not see this netmask of that, because you'll see a smaller subnet since they've broken it down by building or by network instead. But the point is, this entire space, the entire /8, is available on campus. Even though you're currently connected to a smaller subset of that, it's all still available. And as I said earlier, there's the network and the broadcast that subtract from that total number of hosts. The network is what you just use to identify that network, and the broadcast is the address you send to talk to every host on the network, which can be done in special occasions. There's also multicast, but that's a whole other beast, and we won't talk about that. Another one here is one of Iowa State's internet addresses that they own and have purchased. This /16.129.186.0.1 to that. And that's 65,534 hosts. That's one you'll get if you net read your computer without the NAT. You might get one of those. A lot of the servers in many of the buildings are on this range, and you might see that if you try to do a lookup. So public versus private addresses. RFC 1918 defines 3 ranges as reserved for private networks. As you saw in the last slide, the 10.0/8. That Iowa State uses for their internal stuff, that's a private network reserved by the RFC 1918, and as well as the 172.16, and the one you've probably seen the most commonly, which is default on a lot of home routers, is 192.168, and that's a /16 as well. You can pick any range out of that. And of course, Iowa State makes it fun and confusing by having addresses that are similar. So 192.168 is basically 129.186 backwards, so it's kind of confusing to look at those two and figure that out. They also own a 192.188 address, which looks kind of like that, which is confusing. So yeah, those are the private networks. If you're setting up your own business network or home network, you're going to want to pick one of these so you don't conflict with the real internet. And you're free to pick any subnet on these ranges. So you could do 192.168.1.0/24, which would give you 254 addresses, or you could pick 192.168.200. It doesn't really matter. As long as there's no conflicts on your network, it doesn't really matter what range you pick. So now we're going to talk about routing, which is very important to how the internet works and how lots of other smaller networks work inside Iowa State as well. So you can see here we have essentially 3 different networks that are separated by routers. Note that there are no firewalls, there's no fancy stuff going on, this is all routed. So basically how this works is that each device in the network has to know how to talk to the adjacent network. So we have something called routing tables on every single device, which tell that device where to send to next. So if we look at PC0 here, let's say PC0 wants to talk to a device in the 172.18 range. So its routing table is going to point to the nearest router, which is router 0 here. And we can see that in the routing table. Its next hop to that range is router 0. Same thing if you want to talk to this subnet, 172.20 from PC0. Its next hop is going to be router 0 as well. Since it can't just skip ahead and talk to something else, it has to go through its first next hop. And lastly here, if it wants to talk to a device on its own network, it doesn't need to go to a next hop besides just the next device. Since it's on the same local network, it can just talk directly to server 0, for example. It doesn't need to go through a router first. It will pass through a switch, but that's not at the same layer as routing. Routing is done at layer 3, switching is done at layer 2. The network and link layers respectively. And additionally, from the routers, from router 0, it's pretty straightforward from here on, but if it also has its own routing table that tells it how to get to each of these other subnets. I'm not going to talk about each one, but that's pretty straightforward as well. And it knows that router 1 is on the same link, and it knows that these are on the same link as it, so it doesn't have to go through another hop first. So given that limited information on routing, can anyone tell me what is wrong with this picture if we say that router 2 can ping router 1 can ping router 2, PC2 can ping router 2, and it can ping router 1, but PC2 cannot ping PC1. What is wrong with this situation? And what can we do to fix it? Any ideas at all? Any random ideas, suggestions at all? Just throw it out there. Go ahead.
So why can't PC2 ping router 1?
Yes, why can't PC2 ping PC1? Yes, so essentially we're missing a route. So what would we have to add to? I guess there's multiple ways it could be wrong, I guess, but let's say it only knows how to ping router 2. So what can we change on PC2 to fix that? I guess you're on the right track, but so we can just add a route to right. So we can add a route to PC2, telling it that the next hop is router 2. So you're pretty much on the right track there. So PC2 didn't know where to go next. It just was kind of idling there in space, didn't know how it should get to this network. Or actually, that might be a typo because, yeah, that's probably a typo, but pretty close, pretty close. And NAT, you probably heard of NAT before. Comes up pretty often on your home network. Basically, it allows you to translate from your internal private addresses to addresses that are on the internet. So on your private network, in this example, they have addresses of 192.168.0. Whatever. And the internet address of that router is 128.128.128.1. And so in order to communicate with a web server, for example, Google.com, Google.com doesn't know how to talk to your home computer at 192.168.0.3. It doesn't know how to talk to that private range, unless they have their own private range, but that's beyond the point. So in order to facilitate this and to allow servers on the internet to talk to your computer on your local NATed network, your local network, we introduced NAT, which when you send out a request to the internet, your router looks at that request, stamps on its own IP address. So instead of having a source address of 192.168.0.3 or whatever you're coming from, it's going to replace that with its own IP address of 128.128.128.1. And so when it gets to Google.com, Google.com will see 128.128.128.1 and not your internal address. And then Google.com will respond to your router, and your router is keeping track of all these things it's doing. So it'll know that, okay, a connection from Google.com coming to this port belongs back at this certain host inside our network. So it's pretty magic how it all works, but it allows us to have large internal networks that can talk to the internet without worrying about any conflicts of IP addresses. Any questions on all the stuff we just talked about with, yeah?
Yeah, so what if those two computers both send a request with the same page?
Sure. So let's say inside 1 and inside 2, which are different computers on our local network, they both request Google.com. We didn't really talk about this, but when you open a connection from a computer, it's going to start the connection in what's called an Ephraim Report, which is an arbitrary high port as the source port. So let's say inside 1 is going to request Google.com with a source port of 30,000, arbitrarily picked. And let's say inside 2 is going to request Google.com, and it's going to pick a source port of 40,000 arbitrarily. The router is going to see that, and it'll keep track of those separately since it knows one came from this address, one came from that address. It'll send them both out separately. And it's got a table that maps all these connections together. So it'll say, okay, port 30,000 on this address and port 40,000 on this address. These connections are open, and I'm waiting for a response. And once it gets the reply back, it does the same thing. So it's going to open its own high port for each connection as well, and it's going to keep track of that. So let's say, again, it keeps the same port of 30,000 for the first one and 40,000 for the second one. When it gets back that reply, it'll know exactly which one to go back to because it's keeping track of those ports, basically.
So if you got the second computer to make a request on the same port as the other computer?
No, so that's the thing. They could actually make requests from the same source port, but the router is going to make that distinction because it's going to use a different port when it makes that new connection. Okay. That's the tricky part. So yeah, I see where you're going, but the router is smarter than that, and it knows not to try to make two connections with the same source port. It's going to make usually it randomizes it differently anyway, so you don't really see what port was even being used on those. It'll just pick its own port for it, but good question though, yeah. Any other questions on any routing or NAT stuff that we just talked about? Okay, and lastly here, talk about some common protocols that you'll see on the internet. there are so many protocols, I'm not going to talk about them all or even a large subset of them, but just to talk about what they are and what layer they kind of fall in. So given the OSI model or the TCP/IP model we talked about earlier, so these are the networking protocol or IP protocols that communicate across the internet. What layer does anyone think that these fall into on the OSI model? If I could go back to that maybe. So if you had to guess, where would IP fall on this model? It kind of says it actually, so it's not the best question, but any guesses? Where does the IP protocol fall in this diagram? Network layer. OK, thank you. Yeah. How about TCP and UDP and ICMP? You might have heard me and Jake talking earlier about ICMP. It really doesn't have a home in terms of the layer. People will argue that it belongs in the network layer. That's what Wikipedia says actually, but I refuse to believe that, and so does Jake. But TCP and UDP are the most common transport layer protocols. Well, I just gave the answer away there, but they're transport protocols, so they kind of determine how connections run. So TCP is explicitly connection-based. When you try to open a web page, it's going to do a three-way handshake to open that connection, and it's always error-free. So if a connection gets dropped or something gets corrupted, it's always going to try to retransmit and figure that out until the data is successfully transmitted. On the contrary, though, UDP is completely connectionless. It operates without any concept of connections at all. It's kind of just sending data and hoping the other end receives it. If it doesn't receive it, too bad. Maybe the application will have logic to retransmit if that's the case, but in general, this protocol is pretty bare bones, and it's useful for things like real-time streaming of voice and video chat. So when you're on a video chat, let's say some of the data gets lost. You don't want to have to wait for that data to get collected again, because you want to talk in real time. So UDP allows some of that data to get lost, but you might see those pixelations during a video stream where some of the data is lost, but some of it's still moving. That's kind of what happens with UDP, because some of it's coming through, some of it's getting lost, but it's not trying to recover that. And ICMP, this is what happens when you run the command ping on any Windows or Mac or Linux system. It's sending an ICMP probe or request and reply. It's mostly behind the scenes. Internet devices will use this to communicate. They'll say, hey, this port that you tried to reach is not open. And that comes back to your computer, and your computer might have an error message that's more user-friendly than just the status code. But it's usually pretty transparent. Unless you're explicitly using the ping command, you won't really see much of ICMP. And then there's protocols like DNS, HTTP, and all of those I listed there. Can anyone guess what layer that those belong on in the OSI or TCP/IP model? Anyone guess? No. So transport was the TCP and UDP. So we're going up a little higher than that. So on this model, where do you think that's HTTP, which is the language, the protocol that your web browser uses to talk to the server, or FTP, which you can use to transfer files? Application layer, yep, you got it. Oops. And to quote Matt Gerst again, DNS is like the address book of the internet. You say, where is google.com, and it returns a number. Sorry, Matt, I had to requote that. And if you were here for the first meeting this semester, that was an entire presentation on DNS, so you probably heard that quote and heard about DNS already, but very important protocol. HTTP, as I mentioned, it's the one that your browser uses to talk to the web server and back. And lastly, there's endless amounts of application layer protocols, FTP, SSH, SMTP for mail, IRC, etc. Too many to name, but that's just the gist of some things that are out there, some things that you might see pretty commonly. Any questions on all that stuff? No questions? All right.